And I will just invite, without any further ado, study group number 1 on stage, and we will discuss particle accelerators. All right. Same situation for you. We have the microphone, and it is now switched on. You have the presenter here. Big button advances. I don't know who starts. There we go. Thank you very much. And without any further ado, to everyone who is watching this now and everyone in the room, my dear study group number 1, the stage and the teachers and the audience remotely is all yours.
Thank you. Okay, good morning, everyone. We are study group 1, and today we're going to present about particle accelerators. So, first of all, let me introduce the member in our team first. So, my name is Supani, and I come from Thailand, and this is Sanjoy from India, Avona from Poland, Nika from Azerbaijan, and Mark from Australia. So, I will hand over to Sanjoy to take about the curriculum.
In this seminar, first presentation was about particle. Now we need to accelerate it. So our presentation about particle accelerator, and we first highlight on curriculum and classroom connections. At first, around the world, there are some basic topics in their curriculum always. There is acceleration, electric fields, magnetic fields, uniform circular motion, electromagnetic induction, and conservation of energy and momentum. We just relate these topics and teach particle accelerators in our classes. Like electric fields exert force on charged particles, and that force accelerates the particles, and the particles then moves in magnetic fields in a circular path. Then electromagnetic force acts between the between the charged particle, and energy conservation also after the collision also conserved, and then a new particle may be created. This way we can introduce particle accelerator in our class. But why it is not active?
What's happening?
Not.
Something wrong.
Next slide. Yes. Yes.
Someone moved the mouse. The mouse has to
Yeah.
stay here,
Yeah.
otherwise
Yeah.
it won't.
Okay. Now, why should particle accelerator be included in the school syllabus? First thing is to encourage the students about the universe. And two main questions may arise there in their mind, that what are we made of and how did the universe begin? And these two questions may answered by understanding the behavior of standard model, that is the fundamental building blocks of our universe. So students must know about the standard models and the particles. So when they know about the standard models, how they get them? For this we have to accelerate the particles through accelerators and create a collision and get the new particles, so they can observe how particles play the roles to creation of universe and how they're made of.
Okay, and the next part is key ideas. So this is the 4 questions that we want students to know about the particle accelerator. The first question is, what is particle accelerators? So the particle accelerator is the machine that use the electromagnetic field to make the tiny charged particle to have a high speed and high energy. And we can control them to have a right direction, like a RSC. And this was my thinking about the RSC. So, and next one is, what is their purpose? So students should know that the particle accelerator is used to explore the structure of matter and forces in the universe, like you can see in the standard model. Many elementary particles have found in the LHC. And next is, students should know about that particle accelerator can generate a high energy collisions for particle detector, and it can lead to the physics recovery. Okay, the next question is, how do they work? So the first thing, that electric field. So electric field can use to accelerate the charged particles to make the particle have the high energies. And as we know, magnet. So magnetic field are used to steer the path of the charged particle and focus the charged particle. For example, we can use dipole magnetic to bend the particle beam, and we can use quadrupole to make a beam of particle to make it tight. And there are two types of particle accelerator. First is linear, like LINAC, and circular, like LSC. Okay, and the last question that we want students to know that is, why those machines are important. So first of all, this accelerator can enable to make scientists know about the fundamental physics, such as the discovery of Higgs boson. And not only the physics research, particle accelerator can use like a real-world application, especially the medicine, such as proton therapy and PET scan. Thank you.
Oh, no, it's you.
Hey. Thank you. Good morning all in the audience and at home. My little section is looking at student, I suppose, misconceptions and some of the challenges we have when we deliver information about particle accelerators. Have we got the fancy little doodah? Thank you. Let's have a look. So, first of all, I think one of the main misconceptions students may have is that they may believe that particle accelerators are only linear accelerators. So I think as teachers we have the responsibility and indeed the, I suppose, the enjoyment of being able to present the range and the history of particle accelerators. So you've got your original, the original synchrotron cyclotron. Then you go to your synchrocyclotrons through to your linear accelerators. I've got that out of order, sorry, linear accelerators there, and also to the cutting edge of the plasma wake field. So I find there's so much information there that students may not be aware of that we need to present to them as well. Second one, students may not consider possibly the impact of special relativity. As we know, once particles reach about 0.3 the speed of light, relativistic effects jump in and become more significant. And so the type of features we're looking at, for example, might be the frequency tuning of the synchrocyclotron, I say that wrong, the size of the drift tubes in the LINACs, and even the synchronization of the radio frequency signals and the magnetic fields in the booster rings all take into consideration relativistic effects. Another one, please, is the students may not appreciate the limitation of particle accelerators. They may be thinking, why do we not just stick with a cyclotron? And we can explain to them that there's an 80 kilo electron volt limit, that Lorenz's synchrocyclotron, even when it was modified at the end of its life, only got up to 350 mega electron volts. Students need to, I suppose, understand that even the LINACs are limited to their physical length, and booster rings also are limited to their radius as well. And the last one to consider is that students, may believe that particle accelerators are only used in research. I know, for example, in Australia, we've only got one synchrotron. It's a third-generation electron synchrotron light source. It's located in Melbourne. And many students may believe that that's the only application, that it's for research and investigation. Whereas from our work here and our research as well, we realise that there's a large percentage of particle accelerators used for ion implantation and also medical LINACs. And in fact, synchrotron radiation, the one we have in Australia, is internationally 0.2% of its application. So that's just a starting point in terms of students' misconceptions. Thank you.
I would like, hello everyone again. It's really stressful to stay here in front of you. I would like to talk about useful materials and resources that we have found yesterday while preparing presentation. First one, CERN official site, at the same time CERN TV. I think it's heart of the particle physics. Then FET Colorado, they provide different kind of simulations. It is a really good way for students to learn and just try to use the simulations. We found short introduction of particle physics written by Frank Close. We think it is the best way to start with this book and get a lot of information. Allphysics.com, they provide a lot of animations for particle physics. It's interesting tool. And if you are really interested and curious about what is happening there, Vista tool is showing real animations or real data. And last one is Fermi Laboratories. They provide a lot of information in their sites about particle physics, at the same time accelerators. Thank you.
Next part is a best practice example. One of them connect to real life. For example, cancer, radiotherapy, semiconductor manufacturing, material science and drug development, sterilization and food preservation. Only a smart fraction of accelerators are used for fundamental research. Most are tools for industry and medicine. Second proposition is use visuals and tools. For example, a generator, Van Graph, and hands-on models. Simplify step by step. It is best practice example 2. We start with simple ideas and only later move on to more complex ones. Encourage exploration. Let students explore and experiment openly. Use interactive tools to spark curiosity and discovery. The proposition for best practice example is support all learns. Show the right hand roll. Use diagrams of magnets. A best practice examples are a powerful way to inspire students and help them explore the world of science. Thank you.
All right, thank you very much. Any final words about this final slide, or? You don't have to hide even further. It's okay. The stage is still yours. Don't worry. Okay.
Who would like to say something?
Microphone, please. Microphone.
Thanks for this inspirational program that you did for us. It was really great to be here. Would you like to say something?
That's good. I suppose, Jeff, also in closing, just to thank the other participants for sharing their wisdom, their experience, and what they do in their schools and their countries. It's been really invaluable outside of the sessions just to chat with people and to glean information, share resources. So thank you all.
Okay. Well, sorry, I don't want to force you to say anything else. It's just that the idea of this final slide was that you can, that you can say whatever you want to say at the end. So perfectly fine to just have it on the slides. And we are a little bit over time. Timekeeping is an issue today. Any questions in the room? I will take the microphone off you to bring it to whoever has a question. Thank you very much. Thank you, Peter.
So pretend I'm a young student where I say, why don't we study a particle standing still so we really can get its information? Why do we need to accelerate it? What would you tell them?
Oh, love it. Thank you very much.
Particle needs to accelerate because we can tell them that if they don't collide, how to break it. They knows that protons and neutrons are made with quarks, but how the quarks they get, we have to break it. So to break it, we need to collide it. That's why we accelerate it, and then it can from this part after collision, may new particle be born. That's why we can. That's the way we can say the students.
Okay. Any other questions? Yes, Sunny, I'm coming to you. There you go.
Thank you for your talk. So if I were a student in your class and I thought accelerators were so cool and I asked, could we please make one in the classroom, how would you respond?
I love it.
Great question, Sunny. I'd probably grab my Perimeter Institute experiment and get out the aluminium foil, the batteries and magnets, and try and look at that type of, as a modelling example to show and explain that it's very difficult to model the large, the large exceptions. The question that Pete had before also, I think if you want to look at the properties of charged particles, to get them to interact with electric fields, magnetic fields, movement's pretty important to be able to see what happens. Yeah.
All right. And maybe just from my side, because I like your resources you had, and I just wanted to highlight one additional resource that I haven't seen on the slides at least, and I'm not sure if anyone in the room has seen it. It has been produced a few years ago. It's called Accelerator. So Accelerator, the last two letters are AR, which stands for Augmented Reality. I will link it to our program website as well. I like it very much because what it is you can download sheets of paper that you print out, and you can make them into a cube. So you have printouts for a cube, and each of the cube has a special logo on it. And if you then go to the Accelerator app, which is freely available, your students can scan the cube, and each cube represents, for example, a dipole, a quadrupole, a particle source. And if you have different cubes that you have physically on your table, your students can scan them with their phone, and they see an augmented reality particle accelerator. They can even make a circular accelerator by putting the blocks in a circular shape and run them around. I love this resource very much, and since it was not presented during the 2-week program, it was my mental note that should it not show up on the presentation, that I want to mention it because I really like this myself, so I want you to have fun with this as well. So just wanted to mention this. It's really awesome because you can make then, coming back to Sunny's question, you can do very physical accelerators or you can use augmented reality, which can even be interesting for students. All right, we're a little bit behind schedule, so we're making great progress. Let's give study group number 1 a big round of applause. Thank you very much.